When we start to organize quantitative data, remember quantitative data is the data where it has numbers involved, that arithmetic means something. For discrete data, just as a reminder again, discrete data is your countable data. This is when you won't really have like fractions or decimals, because these are things we can count instead of measure. This is our discrete data. If data are discrete with relatively few values of the variable, then the categories of data, which are called the classes of the data, you're going to hear that a lot, the classes will be the different observations. If the data is discrete, but we have a whole lot of different observations, then we can use intervals of numbers instead of just the actual observations themselves. We're going to see this in example 3, so don't really worry about it yet. That's for when we have lots of data and we need to make it actually manageable to see. Example 1 wants us to construct a frequency and relative frequency distribution from discrete data. We did frequency and relative frequency distributions last class for our qualitative data. These can also be done for quantitative data. So here, the manager of a Wendy's fast food restaurant wants to know the typical number of customers who arrive during the lunch hour. The data in Table 8 represent the number of customers who arrive at Wendy's for 40 randomly selected 15-minute intervals of time during lunch. So for example, during one 15-minute interval, 7 customers arrived. So we wrote the number 7. So what we're going to do first is construct a frequency and relative frequency distribution for the data. Question, what did we do last class to do a frequency distribution? It has to do with maybe this column.
We marked down how many times the numbers on there.
Yeah, last class it was like the body parts that this PT had been helping. And so now this time our class, which is our number of customers in each observation, we're going to count how many times we see them throughout this list. Now, there are 40 observations here because there's 40 different randomly selected 15-minute intervals that we're using. I'll start this, but I'm going to have you keep going, and then I'll clean up the answers at the end. But what I would do here is if I see that first observation is 7, I'm going to put a tally mark for 7. This time I'm going to go sideways. So sideways on this table, the next observation is 6, and then 6, and then 6, and then 4, and then 6. So if I was doing that, it would be 3 6s, a 4, and a 6, then a 2, and a 6. So we're making these tallies. Y'all know with tallies, like, have y'all used tallies before? Okay, so once you get to 5, put a cross. The 5 goes across so we can easily count. Okay, I did the first row. Let's have you finish it on up. Just make this tally and fill out the frequency column of this frequency distribution. If you look up at the board, I have the tally and the frequency distribution listed. Again, if I didn't give you enough time to go through it because it's kind of hard to keep track of all those numbers. We get the idea though, we're tallying up the number of times we see that observation in our study. The third column called frequency is a frequency distribution. Review from last class. If I added up all of these numbers, what should it be equal to? It should be equal to the number of observations in my study. So we said that we are doing 40 random intervals. So the frequency should add up to what number here? 40, which it does. When we did relative frequency, that was seeing how often, what percentage of the observations that happened. So when we did relative frequency, review from last class, what we did is we did the frequency divided by the total number of observations. So for the first one, it would be 1 divided by 40, which is 0.025. The second one, we would do 6 divided by 40, and then 1 divided by 40, 4 divided by 40, on and on and on, all the way down our table. Again, I'm going to give you a chance to do this, which means if you haven't grabbed your calculator yet, you're probably going to want to do that. We'll fill out the relative frequency for this discrete data. Okay, again, I may not have given you enough time to finish, but hopefully you did some of them so you can see how this is created. So we have a relative frequency, which are like the percentages of the amount of observations that we see that particular observation. If we added up all of the numbers in the relative frequency, they should add up to 1, because that would all add up to 40 over 40. Yes?
The sixth one, I got
6 out of 40? I could be wrong.
12 out of 40.
For 6? Oh, you know why? Because this should actually be 11. Y'all trusted me. Did you have 11 and you're just like, oh, I must have counted wrong? Yeah. My bad. Remember how I said it should add up to 40? I probably should have checked considering it would have added up to 41. I was just trying to see if you could catch my mistake. Totally. But now if we do 11 over 40, does it come out to the number I have? Yeah. Okay. Thank you so much for saying something so I don't look foolish. Yeah, my bad for making you second guess your counting abilities. So on the basis of these relative frequencies, what percentage of the 15-minute intervals had 6 customers arrive at Wendy's during the lunch hour? So if we're looking at the relative frequencies and 6, that means that 27.5% of these 15-minute intervals had 6 customers arrive at Wendy's during the lunch hour, which is about a little over a quarter of the time. So we can draw nice conclusions from a frequency or a relative frequency distribution. So those are 2 vocabulary terms now that we've seen in 2 days. We can use these types of distributions for both quantitative and qualitative data. Just like last class, we used pictures to describe or to show our data, which sometimes is an easier way to compare or to see them. So just like with bar graphs for qualitative data, quantitative data can be shown in what's called a histogram. You guys, without me telling you it was called a histogram, would have called these bar graphs. They look the exact same, but since this is representing different kind of data, these are called histograms. The height of each rectangle is the frequency or relative frequency of the class, and the width of each rectangle is the same, and the rectangles touch each other. This is similar to the bar graph for qualitative data. So in a histogram, here's what it might look like. So the number of customers we had frequency-wise for 1, we had 1 customer. So we have a bar of 1. For 2, there were 6. So we're going to continue our bar graph, our histogram, at 2. Notice this time, I'm not just using my highlighter because I actually want the width to be good. Your highlighters might be wide enough where you can just have them next to each other. We do want the columns to touch. My iPad's pencil is not wide enough for that, so I'm going to have to actually draw these rectangles. For 3, we had 1. For 4, we had 4. For 5, we had 7. For 6, we had 11, not 12, Miss Quigley, 11. LOL, that's a terrible one. Let me try that again. 7 was 5. Again, this is the data from the front page. I just know you'd have to flip over to see it. 8 customers occurred 2 times. 9 customers occurred 2 times. We never saw 10 customers come in. And 1 time we saw 11 customers. So this is the the frequency distribution in a histogram for the arrivals at Wendy's. I'm coloring mine in because they look better that way. We can also do one of these histograms for the relative frequencies. So that was the last column, the 4th column on the other page. And again, I know you'd have to flip back and forth to see it, so I will tell you the numbers we had. For number of customers being 1, that happened 0.025. 0.025 would make it about here-ish. 2 customers occurred 1.5. 3 customers, 0.025 again. 4 customers, 0.1. 5 customers, 1.75. 6 customers, 2.75. Or sorry, 0.275. Yikes. 7, 1.25, 8, 0.05, 9.05, 10, nothing, and 11.025. Okay, tell him to come by my classroom. Okay. So again, some interesting things about the histogram is that they do need to be touching each other because we're going to draw some conclusions later on in this chapter and describe these shapes. And so it's very helpful if we actually have them touching each other. Feels a lot like the bar graphs we did last class. I agree. Histograms, though, are all smushed next to each other. So it's actually a good place to pause. I know we have like 2 minutes to lunch, but we're going to pause here. After lunch, we'll keep going. One last thing, I guess, before we go, though. What do you notice about the shapes of both of these distributions now that we see it in the bar graph? They're like the same. They're the same kind of distribution because they're representing the same data. We're just getting different numbers, whether it's the raw data of how many times we see it, the frequency, or the percentage out of that frequency. They end up being the same shape, which is really kind of cool when we see them in a histogram. So first part of today, we talked about discrete data, which is data you can count. We're going to start talking about continuous data, which is going to be data in general that we measure or that has decimals and fractions and different things like that. So classes in these types of data are usually going to be intervals of numbers. This is what the little hint we talked about earlier. So our classes this time are going to be intervals. Notice that the data are categorized or groups in these intervals. Each interval represents a class. Each class has what's called a lower class limit, which is the smallest value within the class, and an upper class limit, which is the largest value within the class. The classes should not and do not overlap. This is necessary to avoid confusion as to which class a data value belongs to. Class widths are equal for all classes. So the interval length is called the class width. One exception to the requirement of equal class widths occurs in what's called an open-ended table. A table is open-ended if the first class has no lower limit or the last class has no upper limit. So it's like you get like a little ... and continue on one direction. So if we look at these two examples of tables with classes, the first question is this table open-ended? Do we have a for sure stopping point at the bottom and at the top for this one? Yeah, so this is not open-ended. But we can figure out the class width. How wide is each class? Like how many ages fit into each class here? Yeah, this one's weird. I would actually count these because we have age 15, 16, 17, 18, and 19. So even though 19 minus 15 is 4, there are 5 ages that are in that first class, which means the class width is 5. So I would always count, you're fine. I would always count the class width instead of doing arithmetic to subtract them. Right, for this last question, age 44.99999, are we exactly at 45 yet? No, so we don't round up. We are not yet to this category. We are still within this one. So the age of 44.999, which is basically probably like it's the day before your 45th birthday, that is still going to put you in the 40 to 44 category because you're not actually 45 yet. So we don't round these up. We have to actually make it into that category to switch classes. The second table, however, do we see how this one's different from table 10? What's happening down here at the bottom? And over. It's like a ... So we're not just having the class width here. We're saying 65 and all the way up to 100 and whatever, however old the oldest person alive is. So this table is open-ended. And what is its class width? We're going from age 25 to age 44. How many different ages in that category are there? The class width here is 20. So if I count all the ages, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4. That's 20. I lost count on my hand, but you get it. So the age 70 corresponds to which class? Age 70 would be in 65 and over. So the idea of putting these intervals together for our data will really start to look like something actually that we could do when we look at the next page. In this page, in this example, what we're going to do is we're going to take this data from table 12 that represents the total fines, including late penalties in dollars for a simple random sample of 50 parking and camera violations in the city of New York. We're going to construct a frequency and relative frequency distribution of the data using a class width of 25. Everybody underline that right here. We're going to use a class width of 25, which means we should have 25 dollar amounts in each class. We need to know when to start the class. We need to know how to choose the lower limit for the first class. And if you actually look down at the bottom, it's going to tell us how to do that. To choose the lower class limit of the first class, we're going to choose the smallest observation in the data set or a convenient number slightly lower than the smallest observation in that data set. So let's look through table 12. What's the smallest number you see on there? 65 is going to be our lowest ticket price that we have on this table. Now, since we want a class width of 25, what's a pretty convenient number that's like a multiple of 25 we could use as our starting lower class limit? It needs to be smaller than 65. I would make it a multiple of 25. That makes it really easy. 50. 50 is a very convenient number to use. Do you have to use 50? No. You get to choose the convenient number you're using. But what we will do here is we'll start our classes off with the dollar amount of 25, come on, Miss Quigley, of $50. And that goes all the way through 74.99 because that's a $25 difference between 50 and basically 75. Okay, the next class is going to start immediately after 74.99, which means our next class is going to go from 75 to 99.99. Do we see how we're building this class width of 25 categories for each of these classes? Now, I specifically know I gave you enough boxes here to fill it all the way through the highest list. But if we were to look at our actual list, the highest number on our list is this 322.61, which means we need to make sure that our list goes all the way through 325 or 324.99. I gave you enough boxes for this to happen, but if you didn't, you were building your own, you need to make sure you get through that highest number in your classes. So if we start just like rattling this off, after 99.99, we'd have 100 through 124.99. We'd have 125 to 149.99, 150. See how this is working? 174.99. 175 through 199.99. That's hard to say out loud. 200 through 24.99. 250. Nope. Every single time I do this problem, I do that. 225 through 249.99. 250 to 274.99. 275 through 299.99, and lastly 300 through that upper class limit so that we make sure we get everything, 324.99. Yes?
From where are you getting the numbers on the right?
I'm counting up 25 numbers. 25 numbers higher than 50 is 75. So the last number in the upper class limit for the one above it needs to be minutely smaller. So what is just 1 cent under $75? $74.99. What is 1 cent under $100? $99.99. 1 cent under 125 is $124.99. Because we can't make the list 50 to 75, 75 to 100. Otherwise, 75 is on the list twice. We have to go just underneath it. Does that make sense? That was a great question. Once we have established all of our class intervals, the lower and upper class limits, we go back to the ideas from the first example and we do a tally so that we can do a frequency distribution and a relative frequency distribution. This one's a little bit more challenging, so we'll take our time again. The first number on my list is 211.09. Which class does that belong in? Between 200 and 224.99. So our first tally goes down here. I put it in the wrong one. Boom. Yes?
Yeah.
I'm going to give you a few minutes to get started. I want you to get as much through this as possible. See if you can get the tally for the frequency and relative frequency ready. So we've counted the frequencies of these different fees and fines for these different 50 random samples. Now we find the relative frequency. How did we find relative frequency again? Yes, divide the frequency with the total number. So we have a total of 50. So if we did 1 over 50, this would be 0.02. And the reason we want this again is because it creates a percentage, which is very helpful in drawing conclusions and summarizing data, is having a percentage. We're going to speed racer through this one because we've already done this once. You guys get how to make a frequency or relative frequency distribution, yes? We do all of the dividing. We end up with 0.02 for the first one, zeros for the second one, 0.14, 0.20, 0.10, 0.08, 0.26, 0.08, 0.10, zeros, and 0.02. Oh, sorry. So we have all of our relative frequencies for this information. So it's exactly like what we did with the discrete data, except that now we have a step beforehand because we have to put all of the observations into classes. Otherwise, each individual fine would be its own class, and that's like not really helpful. We need to see the range or the intervals of fines. But now that we have the relative frequency distribution, we can answer the last question. It says from the frequency distribution, we conclude that a fine that was between 200 and 224.99 occurs with the most frequency. And now that we have our relative frequency, we can say the percentage. This is 26% of the fines. I'll rewrite that numbers in a second. This is the Let's say you were not given the class width for the problem that we just did, but we did find the largest data value and the smallest data value. From our actual raw data, the largest value we had on there, and I'm just going to come up here in this little like blank space to do this. The largest number we had was 322.61. And if we subtract the smallest value, which was that 65, and then divide it by the total number of classes, so like let's say we knew we wanted to make 11 classes and we needed to know how wide to make our class width. For some reason we chose 11. If we do that math, 322.61 minus 65 divided by 11 gives you 23.41. So what's a very convenient number to use if our class width should be about 23? 25, which is what we did. So your class width is going to depend on how many categories you want, how many classes you want, or you can be given a class width and then determine the number of categories. So it just depends on what you want out of your data, how you want to display it. Maybe you only have 10 steps in a table, and so you're looking for that. But we can take this continuous data in the same way we did discrete data, and we can make histograms. Oh, look, I already did it for you. I'm so nice. And so we can, again, make the same kind of histograms that we did for discrete data. Any questions? We get how we would have done this if I made you do it by hand? Great. Here's the thing, though. You can do them on your calculator. We're not going to stop and do this now. Well, we just lost a lot of time with that phone call. I don't know if we'll have enough time to do this, but I want you to keep these steps in mind because we're going to use a lot of the calculators later on in this class. So we need to make sure we know how to do these steps. It will actually make a histogram for you, and it's really pretty cool. I think I have it still saved on my personal calculator from when I did it last night, so I'll come around and show everybody. But the steps are all here, and it uses probably a setting you've never done before. We're just not going to do it because you have to type in all 50 data points, and honestly, no thank you right now, right? Okay, if you're interested, it's pretty cool. I'll come around and show you later what it looks like. But we're going to move on. The other type of data you can use to display continuous data is called a dot plot. I personally have not seen these used a lot, but you totally can use them. You make them by placing each observation horizontally in increasing order, which I've done for you. Here's the number of customers from the Wendy's example. And then placing a dot above the observation each time it is observed. So it's kind of like your tally mark, but your tally mark put immediately into a dot plot. So if we were to look at the data from Wendy's, I'm going to look at it because I can flip back in my page pretty quickly. The data from Wendy's, the very first data point we had was that there were 7 customers. So I would have put a dot at 7 and like literally straight up a dot. The next data point was 6, and then another 6, and then another 6, and then a 4. So see how this is what we did with our tallies? But now we're just doing this with a dot plot. After that one, we had 6, and then 2, and then another 6. So as I'm tallying these up, they kind of look like they're becoming these histograms or these bar charts, which is pretty nice because now immediately our tally means something to us. If we were going to go through and actually see the whole thing, I'm not going in order on the table anymore. There was one observation that had 1. There was 6 observations that had 2. 1 observation for 3, 4 observations for 4, 7 observations for 5. There ended up being 11, so I've already done 5, 6, 7, 8, 9, 10, 11. There were 5 for 7, 2 for 8, 2 for 9, and 1 for 11. So our tally marks, when we're looking at the data, can be immediately put into a dot plot, which do look similar to the shapes of our histograms. Again, I haven't seen a dot plot used all that often, but they're kind of cute. Kind of like it. But what we will start to do is start to describe the shape of these different distributions when they're in our histograms. This is a very classic way to describe data. In fact, we're going to be using these distributions throughout the entire course. If we look at the shape of the distribution or the shape of the histogram, there are really 4 options that we're going to work on. What can you tell me about the uniform distribution? What do you notice? Do we notice nothing?
They're all the same.
They're all the same. That's what uniform means. All the same. Great. A bell-shaped curve is asymmetric, just like uniform, and in fact, it creates a bell shape. Don't overthink it. If you followed this data up and down, you see how it kind of creates this like, whoa, this hill. It's called a bell shape. It's a bell curve. But our bell curves are maybe not always perfectly symmetric. So let's say we have something like we can see down on graph C. This is called skewed right. Have we ever heard the word skewed before? It means like to the side. So this is skewed to the right. So that means we have more things tailing off to the right side. The graph has a tail basically on the right side. It's skewed right. For skewed left, it's the same concept except that our like bell curve has a longer tail on the left side. So those are non-uniform distributions. Our 2 uniform distributions are two symmetric, are uniform and bell-shaped, and then you have our skewed or non-uniform distributions. Now, of course, these are not the only displays of data we can use for quantitative data. In our next section, which we're going to do immediately, we're going to talk about additional displays of quantitative data, so these 2 sections go hand in hand.